I want to tell you the story of Einstein's most cited paper. And this story of the paper, which is interesting in itself, is entangled with the story of entanglement. And I would like, so this will be a mixed talk, a little bit history, but a little bit of science as well. Now, do I know how to? Good. So this is the most cited paper of Albert Einstein. It appeared, it's known as the EPR paper, written by Einstein, Podolsky, and Rosen. It appeared in 1935, as you can see, and it has in physical review, and it has an unusual title, which I'll read for you. Can quantum mechanical description of physical reality be considered complete? That I marked in yellow the words which are usually you don't usually find in physical review articles, and it sounds as if the paper is really a little bit about metaphysics or philosophy. So it deals with the issue of what is physical reality and what is the notion of completeness. This is not something physicists normally worry about. I copied below the paper a picture of what Google Scholar says about the paper. And as you can see, this is the most, this appears down here on the screen. It's the most cited paper of Albert Einstein. And I think it is also has a good chance of being the most cited paper in physics. It is remarkable that this paper is the most cited paper of Einstein and not, say, any of his papers either on the special theory of relativity or the general theory of relativity, or the paper for, or the work for which he got the Nobel Prize, the photoelectric effect, or any of the 5 papers in the Annum Mirabilis 1905. And I think part of the reason that this paper is the most quoted paper is that the other papers I mentioned of Einstein got canonized pretty early. And nobody refers today, when one writes something about general relativity, to Einstein's paper, rather one refers to some standard books. But this paper of the EPR paper was not canonized. And in fact, it was controversial for many years and still is. And I think this is an example where sometimes asking a good question reverberates longer than giving a wonderful answer, which essentially, how would you say? I wouldn't say close the field because this is not the right expression, but anyway, this is the most cited paper. Okay, the reason the paper is so much cited, and especially it is so much cited today, is because this is the paper that introduced the notion of entanglement into quantum mechanics. Actually, this is not a precise statement. The word entanglement does not appear in the paper, but the paper makes use of entanglement in a way that really shows the remarkable properties of entanglement. And since entanglement is now considered by many as a hallmark of things which are behind the modern quantum technology, I think this is one of the reasons why the paper is still going strong and being quoted heavily even today. As I mentioned, the word entanglement did not appear in the paper itself, but it appeared for the first time in a private letter written in German that Schrödinger wrote to Einstein. And in a subsequent paper which he published, he noted the following thing, which I want to read, that the entanglement, by the way, he both coined, when he wrote to Einstein, he wrote in German, and then he turned the notion of entanglement Verschränkung, but he also coined the term in English, entanglement. And this he did in a paper which I want to read just one sentence from this paper, where Einstein says that entanglement is the characteristic trait of quantum mechanics that enforces its entire departure from classical lines of thought. And I think it was really due to Schrödinger, the realization that the important thing about quantum mechanics is that the wave function is not a function in ordinary space time that we recognize. It's a function on a huge number of variables out to the 3n, where n is the number of particles. And in this way, it departs from other field theory, classical field theories that were known to everybody. And I think in some ways, the way that I've been taught quantum mechanics in the first year, and they taught us about Schrödinger equation for one particle, this is really taking some of the gist or some of the important issues in quantum mechanics when you just look at one body Schrödinger equation. And the remarkable thing about entanglement, which Einstein note in this letter to Max Born, is this what he called the spukhafte Fernwirkung, which is a spooky action at a distance. And I will come back to this issue of spooky action at a distance, especially since this gave rise in the popular literature to nonsense statements about entanglement, that it allows communication faster than the speed of light. Okay, now I want to go back a few years and start with the establishment of the Institute of Advanced Study in Princeton, 1930. On the left, you see the only picture I could find in Google Images of Princeton in 1930, and it looks rather dreary, I'm afraid. And on the right, you see the announcement in the newspaper about the donation by Louis Bamberger and Mrs. Fulde, who is his sister, who gave $5 million to establish the Institute of Advanced Study. They appointed Abraham Flexner, who was a well-known American educator, to head the institute. And I want to read to you a passage from an article written by Abraham Flexner in the journal Atlantic. And I think it is nice because some words don't lose their significance even 100 years after they are written. So the title of the paper is The Usefulness of Useless Knowledge. And let me read a section. I'm sorry, I apologize for my strong Israeli accent. In a world steeped in irrational hatred, men and women, old and young, detach themselves from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. Unless the world is made a better world, a fairer world, millions will continue to go to the graves silent, saddened, and embittered. Now, 3 years later, in 1933, Einstein made his third trip to America. And on the left picture, you see a famous picture of Einstein riding a bike in Caltech. I think you can recognize the place. And this visit of Einstein to America was auspicious in the sense that it coincided with the rise of Hitler of Nazi Germany. Hitler came to power in January, was appointed the chancellor in January 1933, and it didn't take him a long time to, in about I think it around March or so, the the Nazi government issued this new law, Berufsbeamtes Gesetz, which is the restoration of professional civil service. This is I don't even know if I can call it a euphemism, but it's basically the law stipulated that all, for example, professors in German universities who were tenured, and in fact, all civil servants in the German government who were of non-Aryan origin were dismissed from their jobs. And Einstein was at the time in the States, and this, of course, made it easy for him to decide not to return to Germany. He did return to Europe and sent a letter of resignation to the Prussian Academy of Science. And in the bottom, you can see I made a short quote from this letter. The current state of affairs in Germany compels me to resign herewith from my position at the Prussian Academy of Science. I consider my position's inherent dependence upon the Prussian government intolerable. So in 1934, Einstein was given a position at the Institute of Advanced Study, and he was allowed to hire 2 assistants. One of them is Boris Podolsky, and the other one is Nathan Rosen. I put it down a quote. Boris Podolsky, I'll tell you a little bit about Boris Podolsky later. He got his PhD from Caltech, and Nathan Rosen got his PhD from MIT. At the time, Nathan Rosen was about 25, and I think Boris Podolsky was older, probably at the early 30s. There is a letter which Albert Einstein wrote to Avron Flexner asking him to appoint Boris Podolsky. And in this letter, he says, one of the most brilliant of the younger men who had worked and published with Dirac. Nathan Rosen, I think Nathan Rosen was at the time young faculty at Princeton, and Einstein met him at the university and offered him a position. Now, when apparently it was Boris Podolsky who actually did the writing of the EPR paper and sent it to physical review. And shortly before the paper was supposed to appear, Boris Podolsky contacted the New York Times and told him about the paper. And the New York Times ran an article on this paper, which you can see on the left. Einstein attacks quantum theory. Scientists and 2 colleagues find it is not complete, even though correct. See Fuller 1 possible. And Einstein was furious. In the background, you can see a handwritten note by Einstein in German, which was apparently one of the drafts before he sent his protest letter to the New York Times. And I got hold of this letter from Nathan Rosen's son, Joe Rosen, who had a copy of the original paper. I won't read the German, but I will eventually what appeared in the New York Times was the letter of complaint of Mr. Einstein, which let me read it to you. Any information upon which the article Einstein attacks quantum theory in your issue on May 4th is based was given to you without authority. It is my invariable practice to discuss scientific matters only in the appropriate forum, and I deprecate advanced publication of any announcement in regard to such matters in the secular press. I found it remarkable the use of the term secular press in this context. Now, briefly about Mr. Podolsky. Podolsky was born in Russia. He emigrated to the US as a young man. As I mentioned, he got his PhD from Caltech, and after getting his PhD, he moved to Kharkov to work with Landau, Dirac, and Fock, and he did publish an important paper with Dirac. And in 1934, he returned to America and worked with Einstein at the Institute of Advanced Study. As I mentioned, he apparently was the one who actually drafted the EPR paper, and he then, most of his career was in Cincinnati. An interesting, I don't know, side issue about him, it was that during the Second World War, the American intelligence ran, how would you say, the American intelligence ran, was seeking after people whom they suspected were giving, leaking information to Russia, or people who are engaged in espionage. And this project of the American Secret Service was known as the Venona affair. And in Venona, Boris Podolsky is nicknamed as Quantum, and he's presented there as someone who volunteered to give some information, but apparently they never made use of anything that they learned from Mr. Podolsky. At a later stage in his career, Boris Podolsky took a position at Xavier University, which is a Jesuit school. And my friend Asa Auerbach claims that he converted to Catholicism in order to get this position. But I don't know if this is apocryphal or this is an honest statement. About Nathan Rosen, he was born in New York City in 1909, and to parents who immigrated from Russia as well. He got his MIT in 1932 with Slater, and this is important because Slater was, as we know, Slater was interested in many electrons wave functions. So the interest, I think, in many particle wave functions, he got this interest from Slater. In 1935, he wrote two papers with Albert Einstein that are known today, are famous even today. The first one is the EPR paper, which I mentioned, and the other paper, which is very well known, is known as the Einstein-Rosen bridge, which is in the how do you call it, in this popular science literature, is sometimes known as the wormhole. This is a bridge that connects two pieces of the universe in Einstein theory of general relativity. Now, many people around Einstein, and apparently also Nathan Rosen, were either communists or had great interests in the socialist revolution, in the Bolshevik revolution in Russia. And after he had his position in Princeton, he took a position in 1937 in Kiev. He stayed there. It's interesting that in order to get his position, Einstein wrote a letter on his behalf to Molotov, who was the Secretary General of the Communist Party. And anyway, he got a temporary position at the University of Kiev. He came there with his newlywed wife, who was pregnant at the time, and his first son was born, Joe was born in Kiev. The family did not like, his wife didn't, apparently hated being in Kiev, and after a year, she returned to the US, and Nathan Rosen followed her the year after. Now, for me, Nathan Rosen is important because he founded the physics department at the Technion, and he also founded the School of Engineering at the Ben-Gurion universities in the 60s. Below, you can see the picture of the Technion original building, which was built in 1920. And it started as in the German tradition as a professional school, a Fachhochschule for engineers. And in fact, Einstein was really adamant that Palestine does not need professors, it only needs good technicians. But a departure from this policy was made by Nathan Rosen, who in 1953 decided that he will make an bona fide university physics department at the university level at the Technion. Okay, now let me do a little bit of science and tell you what was the Einstein-Podolsky-Rosen argument that quantum mechanics is incomplete. So it's based on a simple identity that is written here, and the identity is on the left side of the identity. You see two particles. One particle belongs to Alice, and one particle belongs to Bob. And on the left-hand side, you see a superposition of states where the superposition is made of states where Alice's particle is at momentum p, then Bob's particle is at momentum minus p. But there is a superposition of all such p's with equal weight, because the weight is just given by a phase. And this is the left-hand side of this identity. On the right-hand side of this identity, you see the same wave function, but expressed in coordinate space. And then it's a superposition of a particle where Alice's particle is in position A and Bob's particle is in position x plus L. So for both sides, you see that the position of Alice's particle is completely unknown and the momentum of Alice's particle is completely unknown. But if Alice knows her either position or momentum, then she also knows what is Bob's position and momentum. So Einstein made the following claim. Alice can predict the location and momentum of Bob's particle without making any mistake and without in any way disturbing Bob's particle. This means this is what Einstein-Podolsky-Rosen defined as element of reality. If you can predict something without disturbing it, then it is part of reality. And therefore, both the momentum and position of Bob's particle are elements of reality. But in quantum mechanics, the position and momentum of a particle do not coexist because of the Heisenberg uncertainty principle. And it follows that quantum mechanics is incomplete. So this was that's the Einstein-Podolsky-Rosen argument. And when Bohr heard about this argument, then Leon Rosenfeld described the reaction of Bohr. It was an onslaught came down as a bolt from the blue. Now, unlike, by the way, the Einstein EPR paper is delightful to read. It's very clear. It is very, the logic is completely straightforward. You can follow every step. Bohr was not known for being such a clear expositor. He was much more woolly. And John Bell said that, indeed, I have very little idea what Niels Bohr meant. But I think at least my understanding, and I think many people understanding of what Bohr's response was to the EPR was that Alice can predict Bob's position or momenta, provided she measures her particle. But to measure her particle, she has to make a choice. She can either measure position or measure momentum. She cannot do both. This is what people call counterfactual. One can summarize, I think, the disagreement between Einstein and Bohr as the disagreement between Bohr was advocate of what can be known, and Einstein was interested in what there is. So good. Now, it's an interesting issue what really bothered Einstein. In this famous Einstein-Bohr correspondence, there is an issue of what really bothered Einstein and what Bohr responded to the issues that bothered Einstein. And there is an amusing quote which I'd like to tell you. This is a quote Pauli said to Bohr. In fact, you wrote that. You erected some dummy Einstein for yourself, which you then knocked down with great pomp. I think in the old days, people were much more, how would you say, forthright, or how would you say, when they're in their writing. And on the right, you see a picture of Pauli and Bohr, I think looking at the tippy top, which is a kind of a top that flips. Now, there were actually three issues about EPR that bothered Einstein. One issue is mentions in a letter to Avron Pay's realism, which is the moon there where nobody looks? So is reality contingent on our observation? And the other issue is a letter Einstein wrote to Bohr, which was the issue of locality. This is what I mentioned before as spukhafte Fernwirkung, that the fact that Alice, by doing something on her particle, can determine what is happening to Bob's particle. And then in another communication of Einstein to Bohr, the issue of determinism, that God does not play dice. I think Einstein himself was a Spinozist. He really liked Spinoza, who was really a great advocate of determinism. And of course, quantum mechanics is not deterministic, but I think the common understanding is that it was not really determinism that bothered Einstein, but rather the issue of locality and realism, and I will try to elaborate about this. Now, there is a common misconception and nonsense that I mentioned before, that some people think that this EPR phenomenon can allow to transmit information faster than the velocity of light, and this is nonsense. And I think John Bell described it rather nicely in terms of a colleague of his, Mr. Bertelsmann, and the story is about Mr. Bertelsmann's socks. So Mr. Bertelsmann was known to have this idiosyncrasy that he would wear socks of different color, say red and green. So if you would look at his right foot and find out that he has a red sock, then you would know that on his left foot he had a green sock. Now, it is clear from this kind of picture that if Mr. Bertelsmann has long trousers and you don't see the color of his sock on either leg, you don't know which sock is on what leg. But if you lift the right trouser and you find the color of the sock, then you know what is the color of the sock on the left leg, even if the left leg is very far, and you know the color instantaneously. But it is clear from this picture that there is no transmission of information from the right sock to the left, from the right leg to the left leg. You know something, but if someone sits just next to the other leg, he still doesn't know anything unless you give him a phone call or unless he look at the sock himself. Now, there is a second part to this argument. So this part was supposed to explain why there is no transmission of information in this EPR phenomenon. But one can go a step further, which illustrates why quantum mechanics is really weird. And this is the fact that in quantum mechanics, the standard understanding of the Copenhagen thought is that actually the sock on the right leg does not have a color until you observe it. So if it does not have a color until you observe it, then the color appears also on the green sock only once the red sock is observed, which really force you into this non-local behavior. So John Bell, I think, formulated these alternatives as the following two possibilities. Either you think about it classically as Mr. Bertelsmann's socks, so that there is a pre-existing reality of which sock sits where, but there is a hidden variable. The hidden variable is Mr. Bertelsmann himself, who remembers what he did in the morning, or that there is reality is emergent, and the reality only emerges by the action of observation. But if that is the case, then there is action at the distance, or this spukhafte Fernwirkung. And so here is a quote from a letter of Einstein to Lanczos. It seems hard to sneak a look at God's cards, but that he plays dice and uses telepathic method is something that I cannot believe for a single moment. How am I doing with time?
I think you have like 15 more minutes.
Okay, so I think I'll skip this. I think there is a lingering uneasiness with regard to this notion of reality in quantum mechanics. And here are some quotes that I like. David Merman coined the statement, shut up and calculate. And Richard Feynman said, nobody understands quantum mechanics. He said it actually in an interesting, he was asked, he commented on a statement which one often sees that, say in the popular press, people say that few people understand, say, the theory of relativity. And then Feynman retorted that he thinks that there was no period in history where few people understand the theory of relativity. There was a period when one person understood the theory of relativity, and once he wrote the paper, many people understood it. But in contrast with this, nobody understands quantum mechanics. And I think this is basically this issue of reality and action at a distance. Asher Perez, who was my teacher, said that quantum mechanics need no interpretation. And I think the most remarkable statement is by Erwin Schrödinger, who says at some point, I don't like it. I'm sorry I had anything to do with it. Good. Since in view of time, I think I'll skip this and I'll skip that. So let me first give a definition of what does one mean by entanglement. So in quantum mechanics, one distinguishes two kinds of states. The separable states are written here on the top. So here with positive probability, you look at the state which is a product of a pure state of Alice and a pure state of Bob. And any state which you can make by a convex combination of states is called a separable state. So what do I mean by this? Say, with some probability, you tell Alice to pick the state psi A, and you tell Bob to pick some other state. And then with some other probability, you tell Alice to pick another state and Bob to pick another state. And you generate states of these kinds. These states are in the analog of probability measures in classical probability. But the most general density matrix that you can make does not necessarily need to have this form. Or if you want to write it in this form, you may be forced to take p's which are not positive, so it will not be positive probabilities. And in general, it's a convex sum of states which themselves are superposition and not pure product states. Now, by definition, entangled states are all those density matrices which are not separable. So it is defined in a negative way. And you can think of them as states that have no analog, no classical analog. And a typical example is what is known as the Bell state, which is the 0, 0 plus 1, 1. So I'll try to conclude by showing you a beautiful example of these weird properties of quantum mechanics by looking at an example of a entangled states with really remarkable properties. So I present it as a game. The game is known as the GHZ game after Greenberger, Horn, and Zeilinger. And the game is a cooperative game of Alice, Bob, and Charlie against the house. So the game goes like this: that the house asks Alice, Bob, and Charlie one of 4 questions. The questions are marked Q1, Q2, Q3, Q4. And each question is of a 2 type. So it can ask Alice the question X, or it can ask Alice a question Y. There are only 2 questions. And similarly, it can ask Bob the question X, or it can ask Bob the question Y, and similarly for Charlie. Now, Alice and Bob and Charlie have to give an answer to the question X or Y, which is a number, either +1 or -1. And Alice, Bob, and Charlie would win the game if the product of their answers for question 1 is -1, and the product of their answers for question 2, 3, and 4 is +1. So these are the rules of the game. And the question is, can Alice, Bob, and Charlie win every round? And it is quite easy to see that there is no strategy that wins always. Of course, here is a stupid strategy that wins 3/4 of the time. Alice, Bob, and Charlie decide a priori that whatever question they are being asked, the answer is +1. Then, no matter if they are being asked the question X or the question Y, they give +1. Then they satisfy. They win on question 2, 3, and 4, but they lose on question 1. And it's easy to see that there is no better strategy by the following very simple argument. Look at the column of Alice. In the column of Alice, you see that X appears twice and Y appears twice. So no matter what Alice chooses for X, if she chooses either plus or minus, the product of the column of Alice answers is always 1. And similarly, product of the column of Bob's answers is also 1, and the product of the columns of Charlie is also 1. And therefore, the product of the entry in the table is necessarily +1. But in order to win the game, the product of the terms is, I can first compute the product of the rows and then multiply the rows, and the product of all the rows is -1. So this means that there is no way to fill this table with numbers. However, it is possible to satisfy. Quantum mechanics knows how to win the game 100%. In all rounds, Alice and Bob can win the game. And the way they do it is like this. Alice and Bob share an entangled state, which I'll call this GHZ state under Greenberger, Horn, and Zeilinger. There is a picture of Zeilinger here on the table. And the GHZ state is a state of 3 particles. It's an entangled state because it's a sum, it's a superposition of where all particles are either 0 or all particles are at 1. And so you see one particle, Alice has 1 particle, Bob has 1 particle, and Charlie has 1 particle. And now the game goes like this. Alice, Bob, and Charlie prepare such a state. Alice takes her particle to the isolated room and Bob takes his particle to a second isolated room and Charlie to a third isolated room. I forgot to say, but I think it's obvious that Alice, Bob, and Charlie are not allowed to communicate once they are being asked the question. Otherwise, the game is stupid. So Alice, they don't have, but they now Alice, Bob, and Charlie go with their particles to a isolated room. They are being asked a question. And what Alice, Bob, and Charlie do is they measure a property of their particle. They measure the property X of the particle if they are being asked the question X, and they measure the property Y if they are being asked the question Y. And it turns out that they always win. It is true that for every new round of the game, they need a fresh state to run the game. And I'll give you now a proof that they really win in every round, and the proof is really very simple. X and Y are now the Pauli matrices. So question number 1 is correspond to a situation where Alice measures the X Pauli matrix, Bob measures X, and Charlie measures X. Question number 4 would correspond to the case where Alice and Charlie measure Y and Bob measure X. Now, it is easy to see that all questions commute. And therefore, because all questions commute, I can find joint eigenvectors to these questions. Now, also another fact which is easy to see, because X is a Pauli matrix, its square is 1, and Y, its square is also 1. And as a consequence, the Q has the property that its square is 1, and therefore the answers to the questions Q are always plus minus 1. Now, the GHZ state, which I showed in the previous slide, is such that for question 1, it gives the eigenvalue minus, and for all other questions, it gives the eigenvalue plus, and there is clearly one unique such states, and therefore, if Alice and Bob possess this GHZ state, they win every round of this game. So one sees in this illustration that quantum mechanics doesn't try to fill the table. It only tries to answer the question which is being asked at the time. So I think, so where are we going from this? Now, I think I may say something which is non-orthodox, but I like something I learned from Asher Perez, who said that physics is not an exact science. It is the science of approximation. And I think our experience with physics has always been that we had theories which were a good approximation at the time, and at some later stage in the development of science, they were superseded by more accurate theories which were sometimes conceptually different. And in this context, I'd like to read this last quote by Mr. Einstein. Quantum mechanics is very worthy of regard, but an inner voice tells me that this is not yet the right track. The theory yields much, but it hardly brings us closer to the old one's secret. I, in any case, am convinced that he does not play dice. I think when I retired a few years ago, I was worried that a year after I retire, I will learn that everything I taught my students was false. Well, this didn't happen, but still, there is an interesting lesson I want to mention at the end, a lesson from gravity. And it again concerns the notion of action at a distance. So here is a remarkable thing, which I don't think is very well known, that Newton realized that his theory of gravity cannot be the last word about gravity. And he said it explicitly in a in a letter which he wrote to Bentley, an archbishop who was interested mostly in questions about the theological implication of the theory of gravity. Now, I could read what Newton said. Let me first read it, and then I'll say it in a vernacular way. So, one body may act upon another at a distance through a vacuum without the mediation of anything else, and through which their action or force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters any competent faculty of thinking can ever fall into it. Let me say what Newton really complained about. In Newton's gravitation theory, the gravitational potential is the solution of Laplace equation. Laplacian phi equals the source term. And therefore, if I move the sun an inch from where it is, the gravitational force in the entire universe changes immediately. So there is, first of all, there is action, instantaneous action, and second, there is an action at a distance. And Newton thought that this was a blemish of the theory of gravitation which he made up. And in fact, this blemish was taken away by Einstein's general theory of relativity, which interestingly, conceptually is completely foreign to Newton's theory of gravity. But as a computational tool, Newton's theory of gravity is an excellent approximation to general relativity, except if you are close to black holes. So I think this brings me to the end of my talk. There are some worthwhile references that I want to mention. One, there is a lecture by Jean Bricmont from about 2017. There is an article by David Mermin, Physics Today, and by Abraham Pace in Reviews on Modern Physics. And I want to thank you all. Thank you.